Lecture 6, Global Recycling. Well, we've established that greenhouse gases, substances that absorb infrared radiation going out from the surface of the planet, play a major role in establishing a planet's climate. And the greenhouse gases that I've particularly emphasized as being important for the natural greenhouse effect are water vapor and carbon dioxide. So we want to ask a little bit more about what these substances do in their natural behavior in the planetary system, because as you already know for water, they don't just sit there in the atmosphere. Water comes out as precipitation, it's re-evaporated, it flows through rivers, it goes into underground water aquifers and so on. What do these substances do? We really have some sense of the water cycle already, but what about carbon particularly? So this lecture is going to emphasize the role of carbon, the cycling of carbon through the Earth system, and to a lesser extent water, because we already understand most of what we need to know about water. But carbon dioxide, and carbon in particular, has some very subtle aspects to its behavior that are really important to understand if you want to grasp why it is that we humans have the capability we do to interfere with the climate system. Because you might argue that we just play a very small role in all this, and the numbers suggest that we play a pretty small role. How can we end up making a major impact on climate? And I want to give you some detailed background science, particularly on the behavior of carbon, that will help you to understand this. I want to begin, though, with a distinction, an important distinction. With respect to matter, Earth is basically a closed system. What I mean by that is that any, say, oxygen that the Earth possesses, it's probably possessed since its origin. And that oxygen may be assuming different forms. Sometimes it's part of water, H2O. Sometimes it's O2 in the atmosphere. Sometimes it's incorporated into living things in the carbohydrates we eat as foods. It may move around and change its chemical state, but it's still the same oxygen the Earth has had all the time. The Earth has iron in its core and throughout its lithosphere, its rocky material. Some of that iron gets incorporated into the hemoglobin of our blood and then returns to the natural systems when we die and decay. That's iron cycling around through the natural system. Most materials do that. They undergo natural cycles. But with respect to these materials, the Earth is a closed system. And I want to contrast that with energy, which has formed an important, which has been an important player in the first part of the course and is going to become an important player in the last part. With respect to energy, Earth is not a closed system. Energy comes into Earth, almost all of it from the sun, as we'll see in Lecture 10, not quite all of it, but almost all of it comes from the sun. And it goes back out into space in the form of infrared radiation. And to the extent that we are in energy balance, and we are very, very nearly in energy balance, even if it's not perfect, to the extent that we're in energy balance, all the energy that comes to us from the sun is radiated back into space. So the Earth processes energy as sort of a once-through system. The Earth is not a closed system with respect to energy, but with respect to matter, with the exception of a few molecules that occasionally escape off the upper atmosphere into space, and some meteoritic dust which comes down to the atmosphere, and the occasional gas from a comet tail that we pass through, or the occasional spacecraft that we send out into the cosmos never to return to Earth. With those minor exceptions, the materials that make up our planet and its atmosphere and its oceans and its rocks and so on cycle continuously through the Earth atmosphere ocean system. And we need to understand those cycles because it's when some materials, particularly water and carbon dioxide, are in the atmosphere that they exert a greenhouse effect, and when they're not in the atmosphere, they don't. So we need to understand these cycles. Now, there are lots of cycles that are important, as I've suggested. In particular, for climate, the water cycle and the carbon cycle are important. The nitrogen cycle turns out to be important. I mentioned nitrogen, an atmospheric constituent that's largely inert, but it does play an important role, for example, in fertilizing plants. And there are plants that can take nitrogen out of the atmosphere and incorporate it into plant matter, and that makes protein eventually. Lightning strikes can fix nitrogen from the atmosphere into other nitrogen compounds. So there is some cycling of nitrogen through the system. Phosphorus, another nutrient, cycles through the system. Sulfur, and all these things have some effect when they get into the atmosphere, and so they affect climate. But the important ones are water vapor and carbon dioxide. And so those are the only ones I'm going to talk about. And that's because they are present in fairly substantial amounts in the atmosphere compared to many of the other trace substances, and they are strong greenhouse gases. Although what I mean by strong, I'm going to have to explain a little more in a subsequent lecture. So you really know already pretty much what you need to know about the water cycle or the hydrologic cycle. It's basically the cycle whereby water evaporates from the surface of oceans and lakes, rises into the atmosphere, carrying with it that latent heat that I described earlier, maybe moves to a different geographical location, falls as precipitation, typically flows down through the system of rivers and returns to the ocean. So it really is a cycle. That's the water cycle. It's solar energy that ultimately drives that cycle, providing the energy that evaporates the water, making molecules move faster and therefore able to escape the liquid surface and go into the atmosphere as water vapor. That's what drives it. And that makes the rate of evaporation very strongly dependent on temperature. In fact, more strongly dependent than you might think. The rate of evaporation goes up very dramatically with temperature until you reach the boiling point, and evaporation then occurs extraordinarily rapidly as the water turns almost immediately into steam. There's still very little water in the atmosphere. I've mentioned that depending on the humidity, the water in the atmosphere may be as much as a few percent or maybe a fraction of a percent, but that amount is tiny compared to the water that's stored in the oceans and in the cryosphere, that is the body of frozen water. So the liquid water, surface waters, the underground waters, and the waters locked up in ice constitute a far greater fraction of the water. It's only a tiny amount of the total water on Earth that's in the atmosphere. And as I mentioned before, it responds extremely quickly to changing atmospheric conditions. If it gets a little warmer, we get more evaporation. If it gets a little cooler, we get less evaporation, and the water vapor in the atmosphere responds. And one way of thinking about that is to ask this question: how long would a typical water molecule remain in the atmosphere? And the answer, that's called the residence time, the answer for a typical water molecule is a time on the order of a week. So if a water molecule gets evaporated from the surface waters, it finds itself in the atmosphere, and it's likely on average to remain there for a week. Now that's an average. Some water molecule may come out a day later. Someone may be up there for a month. But on the average, the sort of time scale for water vapor to live in the atmosphere or stay in the atmosphere is about a week. And it's up there, and it has not only its waterness, it also has this latent energy associated with the fact that it's in the atmosphere as a vapor, and it can give up that energy if it condenses. It may still be in the atmosphere as a cloud droplet, but eventually it precipitates out as rain or snow. So the water cycle does two things. It contributes to a greenhouse gas that's in the atmosphere, but it cycles rapidly, so the amount of that greenhouse gas can change very rapidly with temperature. And I'll have more to say about that in subsequent lectures when I talk about the human-induced greenhouse effect. And it also contributes to the flow of energy between Earth's surface and atmosphere. So that's the water cycle. And you've all seen pictures of the water cycle with mountains and the water falling down and running down the rivers. And that's pretty well known. The important point I want to emphasize about it is that the water cycle is pretty fast. That water cycles out of the atmosphere on timescales on the order of about a week. And by the way, some of the other cycles I mentioned, the phosphorus cycle, the sulfur cycle, and so on, they also have characteristic time scales for the time that, say, sulfur compounds remain in the atmosphere. It's pretty easy to give an unambiguous answer for some of those substances. Carbon is different. Carbon cycles on many, many different time scales. And so if someone asks, how long does carbon live in the atmosphere? That's a rather subtle question. And I want to spend the rest of this lecture exploring the carbon cycle so we can come to understand the answer to that question, because in the back of my mind is something that's been implicit in everything I've said so far, but I haven't really talked about explicitly. And that is, if we change the carbon dioxide content of the atmosphere, if we increase it in particular, we will strengthen the greenhouse effect and we will cause the planet to warm. Now that isn't describing any details, but it's describing the basic physics of what we should expect happens if we put more carbon dioxide in the atmosphere. And it therefore becomes crucial to understand, if we do put more carbon dioxide in the atmosphere, how long is it going to stay there? How quickly can we turn it off? If we cause the planet to warm up and we don't like that, how quickly can we reverse the situation? If the carbon comes out of the atmosphere in a week like water vapor does, no problem. If it comes out in a year or 5 years, maybe no problem. But if it takes 1,000 years, maybe a problem. So we want to explore that. And the answer I'm going to tell you right off the bat is ambiguous in a subtle, important way that you need to understand why it is we worry about anthropogenic carbon. Carbon cycle is complicated because it involves interactions among a whole lot of regions. The atmosphere interacts directly with the land surface, with the soils and rocks. The atmosphere interacts with the surface of the ocean, particularly through carbon dissolving in the ocean and coming back out of the ocean. And most importantly, perhaps, the carbon in the atmosphere interacts with the biosphere, that is, with the living content of the Earth, by being taken up by plants and being breathed out by plants and animals as they respire. And we want to look at all these processes. There are even geological processes on the longest time scales where carbon interacts in the atmosphere interacts with carbon in the Earth. So the rest of this lecture is going to focus on the carbon cycle, and we're going to look at one diagram that really sums up the entire carbon cycle. And it's a diagram that basically shows amounts of carbon that's stored in different regions of the Earth system. For example, the atmosphere has stored carbon in it. These places that store carbon are called reservoirs. So the atmosphere is a reservoir of carbon. The the biota, the plants and animals, are a reservoir of carbon. The surface waters of the ocean are a reservoir of carbon. The deep ocean is a different reservoir of carbon, different for reasons I'll describe. And among these reservoirs are flows of carbon that go back and forth. And so to understand the question, how long will carbon stay in the atmosphere, we have to understand all these flows that take place between the atmosphere and the biosphere and the atmosphere and the soils and the atmosphere and the ocean and the upper ocean and the lower ocean and so on. And I will say right at the outset,